Let's continue with the part of fluid motion. We were here, right? We are going to talk about ideal fluid flow. Now, first, we would like to introduce a concept that is called steady flow or laminar flow. It means that in the flow, you imagine now I'm inside the liquid, I'm inside the fluid, and you pick up a specific point in space, okay? And the steady flow or the laminar flow means the density and the velocity of the fluid at that specific point do not change. So this is the, for example, the flow of a fluid inside a pipe. The pipe has a shape that may be very complicated, but you just allow the flow to be very complicated. The density, the velocity may change with position. But if I have a steady flow or a laminar flow, that means if I look at the density and the pressure at the density and the velocity at a particular position, I always get the same value. Okay, so if I look here, I measure the density of fluid at time t, and I measure the density of the fluid at another time, which I call t prime, at the same position, I got the same value. And also for the velocity. Okay, so it means I have to, if I measure at the same place and at different times, I got the same physical quantity. I got the same value for the physical quantity. Okay. Now, but imagine now, since the fluid are moving all the time, right? The fluid is in motion. If instead of keeping my location fixed, I can follow a puzzle of fluid. Suppose I'm a small n, okay? And the fluid just carry me forward along the stream, okay? So I now follow the flow of fluid. So at a certain time t, suppose I'm here, right? And at a later time t prime, because of the fluid flowing, I'm carried to another position. Okay, I just follow the fluid flow. I just have the same velocity and as the fluid that surrounds me. Okay, so I go to another position. Now, if you look at the density at these two positions, the initial time is t, the final time is t prime, but I've gone to the different position. So the initial position x, y, z, the final position x prime, y prime, z prime. Okay, there are two different positions, and they will be different even if the flow is steady. Okay, so the steady flow does not guarantee that when you follow a puzzle of liquid, the physical quantity will be unchanged. In fact, the physical quantity will change when you follow the flow along the liquid, along a streamline on the liquid. Okay. And also, of course, the velocity will also change. At this position, the liquid may be flowing a little bit slow, and at other position, the liquid may be flowing faster. Okay, so again, the velocity will not keep constant if you follow the flow. Okay. So in here, we are talking about the same puzzle of liquid. The puzzle means a small packet of liquid. And we just follow the puzzle to different position, and we find different density and different velocity. Okay, when you follow it, you go to the different position, you find the density change and also the volume, and also the velocity change. Is that clear? Now let's have our discussion a little bit abstract. So let's have an analogy. The analogy are the cars driving on the road. but the road has a change in width. Okay, here in this part the road is wider, and here this part of the road is narrower. Okay, so what would you expect the driving speed to change if you have a lot of car coming into the junction? What would you expect? If the cars keep on going without stop, okay, then you will expect, because this road is this part is narrower, the car has to be moving faster in order for not blocking the incoming car, right? So that means if the road is wider, the car is driving slower, and if the road is narrower, then you have the faster you have to drive the car faster in order for a car not accumulating at the junction. Okay. Now suppose the velocity of the car is 20 kilometer per hour at this position, and at another position in the narrow part of the road, the car velocity is 40 kilometer per hour. So if you are sitting on a car, and you follow the car from this position to this position to that position, you have an acceleration. Your speed increased from 20 kilometer per hour to 40 kilometer per hour. That is, you are following a parcel of liquid inside the fluid. That is this case. If you follow the parcel of fluid inside the liquid, from here to here, you have the speed increase, and you also have a density change. Okay, so that is what happens when you follow the motion of a car along the streamline. Okay, but if you are looking at a particular position in the flow, for example, this position, this car may pass, and here come another car. Okay, but if you are looking at this position, but different car, okay, the car comes and passes, you always get the same velocity of 20 kilometer per hour. When you look at this position, the car comes and goes, but as long as you are looking at this position, the car there always has a speed of 40 kilometer per hour. Okay, and that is what is called the steady flow or laminar flow. Okay, is that clear? Now we assume an ideal fluid. What's meant by ideal fluid? An ideal fluid is actually incompressible, so the density remains a constant. Okay, throughout the whole fluid. Now that is true for liquid. I would say oil and water, those liquid, is almost incompressible. They are almost incompressible. It's in fact very difficult to compress liquid. Okay, but for air is actually compressible. But for flow speed, for air speed, that is much smaller than the speed of sound in air. Air can be approximated as an incompressible fluid. Okay, I will not tell you the reason why this is related to the speed of sound, but I told you to tell you the fact. If the speed of sound, if the speed of air, of the flow of air, is much less than the speed of sound in air, then the flow can be regarded as almost incompressible. Okay, so the density remains almost constant throughout the whole fluid. Okay, and also we assume no viscosity, which is of course not true, but we simplify everything. Fluid has viscosity, different viscosity liquid, liquid with different viscosity flow in very differently. If you have honey has a very high viscosity liquid, and it's very difficult for you to make it flow out of a test tube. If you have a liquid that is of a low viscosity, then it's very easily you can make it flow very fluidly out of the test tube. And we also assume no rotational flow. Now, rotational rotation of the liquid is actually largely related to viscosity. I will not tell you the reason why, but if you have a large velocity flow around, say, a obstacle, if you have an object moving fast, for example, in a fluid, a large object moving fast in the fluid, you see when you see the flow passes the object, you will see the vortex developing around that object. Okay, and that's a phenomenon called turbulence. Now, turbulence is actually a very difficult problem in physics. It's very difficult for you to describe it analytically. People have to rely on a lot of computer simulation to describe the turbulence phenomena. And turbulence is usually associated with the formation of a lot of vortex. Okay, so without the vortex, I assume no turbulence inside the fluid. So that's from an ideal fluid flow. And for ideal fluid flow, I have the concept of a streamline for laminar flow. Now, what is a streamline? A streamline is actually a trajectory of the fluid pressure inside the fluid. Suppose I am together with a pressure of fluid here. At this moment, I'm here. But another moment, I'm at another position. And still at another moment, I will be another position, right? I now follow the flow all the way along the stream. Okay, so my trajectory inside the liquid, okay, will form a streamline. The streamline is simply a trajectory of a puzzle of liquid along the flow. Is that clear? Now, but of course, it's not restricted to this streamline. I can have another streamline. I can actually have infinite amount of streamline. Suppose I'm now at another position, and I just follow fluid flow, and that gives me another streamline. So you have many streamlines that form a bundle. Along the fluid. And the velocity of the pressure of liquid is actually tangential to the streamline, because the fluid is now flowing in this direction along the streamline, right? So the velocity direction must be tangential to the streamline. Okay. Now for the steady flow, a steady flow, remember what is a steady flow? A steady flow would not have a change in velocity when I'm looking at a particular position. So the velocity here is always the same. The velocity there is always the same. It will not change with time. Okay, so and that means the streamline will not change with time. For steady flow or laminar flow, so-called laminar flow, because of the fluid flow in layer for steady flow. So that's why it's also called laminar flow. For steady flow or laminar flow, the streamline do not change with time. Okay, because the velocity of flow always takes on a particular value at a certain position. Okay. Now we want to derive an important equation called equation of continuity. Now it is not nothing but only expressed the conservation of fluid volume in the flow. Now we assume that the fluid is incompressible, right? So the amount of fluid, the volume of fluid entering a certain pipe, for example, must be equal to the amount of fluid leaving that pipe. Is that because the volume of liquid is conserved? You cannot compress the liquid inside the pipe, right? So if the fluid is incompressible and you cannot compress the fluid inside the pipe, the water entering must be equal to the water leaving. Okay, that is the amount of water entering, and the volume of water entering must be equal to the volume of water leaving. That is the equation of continuity. And now we want to derive an equation for that. Now let's consider a simple situation when you have an area A here, and the velocity of flow is perpendicular to that area. Okay. Now imagine now I wait for a time delta t. Delta t is a sufficiently small time. How much liquid? What is the volume of liquid that passes through this area? I ask this question. Well, it's easy to formulate the problem. Now imagine if all the liquid here are moving with a velocity v, then the liquid molecule initially at a distance v delta t from the area will move a distance v delta t in the time interval, right? So it will go from here to exactly at the position of the area in a time interval delta t. And you can imagine now all the molecule inside this rectangular volume will move past the area in the time interval delta t. So what is that? This volume? The volume will have a height equal to v delta t and a base area equal to A. In a time delta t, all the liquid inside this volume will move past the area A. Is that right? So delta V, that is the liquid volume here, is equal to the base area, the area A, multiplied by V delta T. That is the volume move passes the area in a time delta T. I divided the equation by delta T, I get dV dt. That is the rate of volume passing through the area. And I find it equal to VA, the volume, the density, the velocity multiplied by the cross-section area. If I multiply the velocity by the area, I got the rate of volume of liquid passing through the area. Okay. Now suppose now I have a tube. The tube has a varying cross-sectional area. Suppose at one end, the tube has a larger cross-sectional area, which I call A1. At the other end, the tube has a smaller cross-sectional area, which I call A2. I want to relate the velocity at the entering when it's entered the tube, and V1, and the velocity V2 when it's leave the tube. By the equation of continuity, this volume will be conserved. dV dt will be the same on both sides, right? I cannot have more water entering than leaving, or more water leaving than entering, right? So the dV dt on both sides must be the same. And that they are equal to what? They are equal to the product of the velocity with the area. So V1 A1 on this side must be equal to V2 A2 on the other side. And they are both equal to the rate of water flow, the rate of volume, the volume rates of water flow. Okay. So this is an important equation for incompressible fluid. Now the equation of continuity actually applies to the whole pipe. Or I can imagine it applies to a bundle of streamline. What is a bundle of streamline? A bundle of streamline is actually imaginary pipes. Now, imagine the concept of streamline that I've just introduced. If I start with a puzzle of liquid here, I follow the puzzle, there's a streamline. I follow another puzzle and I got another streamline, right? So if I follow a lot of puzzle here, I draw a lot of streamline, right? And the streamline span over the whole tube. Is that right? And that is called a bundle of streamline. Is that right? Now, you can see the cross-sectional area of the pipe change, right? Suppose the area here is larger and the area here is smaller. But the number of streamline remain conserved, right? Because for each streamline, I follow all the way from this side to another side. So the number of streamline is the same. But here I have a larger area, and on the other side I have a small area. So that means the density of the streamline may change when I follow the flow. So how would that change? I use the equation of continuity. V1 A1 is equal to V2 A2, right? And it's equal to a constant, and that means the velocity is inversely proportional to the area. So if I have a large area, I have a small velocity. And if I have a small velocity, then if I have a small area, then I have a large velocity. Okay, is that clear? Now, but I know the streamline here is less dense, right? Because you have a larger area. So when the streamline is getting less dense, you have a small velocity. And when the streamline is, when this area is small, A is small and the streamline is getting very close together, the streamline density is high, you have a large velocity. So that means the streamline density expresses the velocity of a fluid flow. When the streamline are getting wider apart, you have a small velocity. When the streamline are getting close to each other, you have a high velocity flow. Okay, so there's a pictorial way to express the velocity. You can look at the streamline density to judge whether the velocity of the flow is high or low at different position. Okay. Now, actually, this concept is very similar to, for example, electric field or gravitational field. In last chapter, we discussed about gravitational field. When the field lines are getting close, okay, when the field line density are getting large, when the lines are very close together, it means a strong field. Is that right? And when the field line diverge, you go further away from the object, the field line density become lower. Okay, and that means the gravitational field strength is smaller. Now the same thing, but with the velocity. When the streamline getting close, you have a high velocity. When the streamline getting farther apart, you have a low velocity. Okay. Now we derive an important equation known as the balloon's equation. Suppose we have an imaginary pipe. Now actually, we don't need the real pipe, a physical pipe that confines the liquid. I can just follow the flow streamline and use the bundle of streamline to construct an imaginary pipe along the fluid. Okay. Now, so we divide the volume in the pipe into three regions: region A, region B, and region C. It happens that region A has the same volume as region C. So you imagine when the liquid moves into volume A, it moves a distance delta x1 with the area A1, pressure P1, velocity V1. So when the fluid moves inside volume A, it displays some water out, right? Because the fluid is incompressible. So when the fluid goes into this volume A, the volume that is originally the water that's originally in volume B will be displaced to volume C. Okay, so the water move out here. So volume A and volume C actually have the same volume, but of course the fluid on these two sides they move different distance because of the difference in cross-sectional area. On the entering side, the fluid move a distance delta x1, but on the side that is leaving, the fluid move another distance delta x2. Okay. Okay, so let's calculate the work done by the external fluid on this column of fluid. Okay, now the column of liquid is actually being pushed by the external by the other liquid from the outside. Okay, you imagine a pipe of fluid. They are sandwiched between the other fluid that is outside the volume. So that other volume of liquid press on this column. Okay, and that produces a work done because the liquid is moving, right? So how to calculate that net work done from the outside? Well, I know that the pressure is P1 here, the area is A1. So I have P1 A1 as a pressure force, right? The pressure force multiplied by the displacement, the force multiplied by the displacement give you the work done. It is a work done by other liquid, by the liquid outside on this column of fluid, pressing the fluid into the volume, advancing by distance delta x1. There's another work done from the other side. This is equal to P2A2 delta x2. But since the pressure force is pressing it inwards, the displacement is outward, the two have opposite direction. So the work done is negative. So I have minus P2A2 delta x2. The pressure is pressing into the column, but the fluid is moving out, so they are opposite direction. So the work done is negative. Now I have used the conservation of volume. The volume in A is equal to volume in C. So A1 multiplied by delta X1 is equal to A2 multiplied by delta X2. And I denote this same volume by V. So now I have P1 minus P2V. That is the work done from the external fluid on this liquid column. Okay. Now I have to relate the work done with the change in energy. Initially, I imagine that the liquid is in volume A and volume B. So the initial energy of these two parts is EA plus EB. EA means the energy, the mechanical energy in volume A. EB means the mechanical energy in volume B. And in the time delta T, somehow the liquid move, right? It moved out of volume A, and it's moved to some liquid in volume B. It moved to volume C. Okay, so the final volume will goes to volume B and volume C. So the final energy involved, the energy in the parts of volume B and volume C. So this is the final energy of the liquid, EB plus EC, and the initial energy is EB plus EA. And the difference in the energy when the fluid moves in this time interval is the difference between the two. And the central part doesn't change. The energy in the central part B doesn't change, so it cancels. And what I got is EC minus EA. The energy of the fluid here in this section minus the energy of fluid in this section A. Is that clear? Now I equate the work done. From the external force to the energy change of the fluid column. Okay, that is a work energy theorem. Sorry. What is EC minus EA? Well, the mechanical energy consists of two parts. The first part is the kinetic energies. And suppose this mass is m. I have the kinetic energy half mv2 squared. And also the potential energy. The potential energy depends on the heights above a certain reference level. And on this part C, the height is h2. So the potential energy is mgh2. We assume the cross section to be small compared with the height. So we don't calculate the variation of heights across the cross section. Okay. So the potential energy and the kinetic energy, these two terms. And for the side A, for the volume A, I also have this. Okay. But the V is V1, the height is H1. So the difference between EC and EA are the difference between these two terms. Now I can extract the common factor rho m out, and the mass of the liquid is simply rho, the density multiplied by the volume. Is that right? So now I have these two terms. All right. And when I equate these two terms with the work done is P1 minus P2V. I have this equation. And you can see the rho, the V will cancel on both sides. And the equation is interesting. It consists of a P half V square and rho GH at two different positions, right? So I can move all the terms in position A to one side, and I can move all the terms that involve position B, position C on the other to the other side. And so what I get is this: P1 plus rho GH1 plus half rho V1 square is equal to P2 plus rho GH2 plus half rho V square, V2 square. So it means what? It means this combination of quantity is a conserved quantity along the field line. Position 1 and position 2 are two different positions along a bundle of streamline. Is that right? And this equation simply say the combination P plus rho GH plus half rho V square is somehow a quantity that is conserved along streamline. You measure this quantity at the beginning. When you enter the type, the tip is equal to that combination of quantity when you lift the tip. Is that okay? Now, but of course, the pressure, the heights or the velocity, they are keep on changing all the way. P1 is not equal to P2. V1 is not equal to V2. But this combination, okay, P plus rho GH plus half rho V squared remains the same on both sides. And it remains the same all the way along the stream of the bundle of streamline. And that is Bernoulli's equation. Okay. Now you can see Bernoulli's equation is nothing, but it expresses the conservation of energy because we use the Atwood energy theorem. The work done from the outside is equal to the change in energy. So it only expresses the conservation of energy in the ideal phase flow. And it can be applied to an ideal phase flow as long as the energy loss due to viscosity, due to friction, etc., is negligible. As long as those loss is negligible, it is a good approximation. Okay. Now let's apply this Bernoulli's principle to this interesting example. When you take an airplane, you see a funny thing, a little thing sticking out from the head of an airplane. Now this is called a pitot tube. A pitot tube is actually an instrument for measuring the speed of flight. Now, how do the instrument measure the speed of flight? Now, this is a simplified diagram showing the internal structure of a pitot tube. Now, this tube is connected to a U-shaped region here, which is filled with a liquid, presumably mercury. Okay, and due to the pressure difference in the two column of air, there is a difference in height h in the mercury column. But what causes the difference in pressure? Now you can see the two sides of the U-tube. They are exposed to air in a different way. For the first tube, the opening of the tube is facing the incoming air. It's directly facing the incoming air. So there's a so-called stagnation point here. The liquid, the fluid, the air just bypasses the tube. Okay, just bypass the tube. And the velocity of flow will become smaller when it's getting close to the opening of the tube. So that becomes a so-called stagnation point. The stagnation point means you have a zero velocity here, exactly at the opening. And the pressure here at the stagnation point is equal to the air pressure inside the tube. Okay. Now, how about the other side? The other side do not have the opening at the end, but the opening is on the side, on one side of the tube. So when the fluid passes, when the air passes, it has a velocity v2. Okay, the velocity v on this side is not zero. So the pressure that this tube is measuring is the pressure when the air is moving with velocity v2. Okay, do you understand? So this forms a difference in pressure, and the difference in pressure will result in the difference in mercury column in the U tube. Okay, so I now apply the Bernoulli's principle. I assume the tube to be very small compared with the heights above the Earth, so I can negate the height. So I don't have to consider the h rho gh term. I only have to consider the p plus half rho v square term. For the opening two that is facing the moving air, I have P2 as its pressure. The velocity is V2, so I have half rho V2 square as the kinetic energy term. Now you can see this is the pressure term, this is kinetic energy. Okay. And for this side, the pressure term is P1, and the velocity is essentially 0. V1 is 0, so I don't have the kinetic energy term. So I now can solve for the velocity V2, which I now call V, right? The velocity of the air, and the velocity of air is just the velocity of airplane, right? Because the motion is relative. When the airplane fly with velocity V, the velocity of air relative to the plane is also V, right? So that means I can measure the velocity of the airplane. The velocity of the airplane after solving this equation is square root 2p1 minus p2 divided by rho. How can I find p1 minus p2? Well, with this difference in height. The difference in pressure is equal to the fluid pressure of the liquid column. That is rho hg, the density of mercury multiplied by G multiplied by H. So with this reading H, I can calculate delta P, and I substitute delta P here, I got V. I know the velocity of the airplane. Higher speed result in a higher pressure difference and a higher difference in the liquid column. Now, this is a historical issue. About 10 years ago, 11 years ago, Air France flight 7477 crashed on June 1 of 2009. Now, in fact, the airplane has a lot of different instruments that try to measure the speed of the airplane. But somehow the pitot tube is getting blocked by the ice cube. Okay, when the airplane fly into a great height, the ice cube block the pitot tube, and that leads to incorrect reading of the pitot tube. And it happens that somehow the other ways of monitoring the speed of the airplane also fail. And so the crew thought that the airplane is not flying within a high enough speed. So they keep on increasing the speed and to a very dangerous level until it's too late to rectify, and the plane crash. And the plane crashed somewhere here in the Atlantic Ocean. Okay, that is a story. That's a real story actually. Now, let me explain a little bit about the airplane leaf. Now, if you look at the cross section of a passenger plane, you take a cross section of that, and you will find that the cross section is not symmetrical. You will find that the base of the airplane, of the wings, is, now this is a wing. If you take a cross section of it, the base of the wings is flatter, and the top and the top part of the wing is more curved. Okay, so at the end is curved slightly downwards. So it's an interesting cross section shape like this. Now, when this wing passes through the air, I find that the velocity of air above the wing is slightly larger than the velocity that flows below the wing. Okay, so V1, which is above the wing, is larger than V2, which flows below the wing. Okay, so there's a difference in velocity. And according to the Bernoulli's equation, now that's not strictly correct, because actually the actual pressure is very difficult to calculate. It has to include the viscosity effect and all that, or the complicated turbulence effect. But essentially, this is the story. If you apply the Bernoulli's equation to a certain approximation, P plus half rho G rho squared is equal to a constant. So if you have a smaller V, if V on the upper side is large, V1 is large, then you have a smaller pressure. So the pressure at the top is very smaller. If you have a larger velocity if a small velocity at the base, if V2 is small, then you have a larger pressure P2. So in this case, you can see the upward pressure at the base is smaller than the downward pressure from the top. So P2 is larger than P1, and so there will be a net upward force that leave the plane, that leave the wings, and that is the lift force that maintain the airplane flying in the sky. Okay, that counterbalance the weights of the plane. Now I show you a wind tube, not a simulation. It's a real experiment actually. So that's why I think it is actually instructive for you to see it, because this is a real thing. Now people actually they put some smoke in the old days, especially when technology is not so advanced. They put the smoke in a wind tube. A wind tube is actually a large tube with airflow to simulate the motion of air in an aerodynamic situation. So this is a cross section of wing. Now you can see with the smoke, you can easily see the streamline passing through the wing. Okay. Now so let's see how the velocity. I better show it like this. Now so what is the velocity upper and lower part? Let's see. We take a snapshot of the whole cross section, and so we can look at the velocity at different parts. Now this is a slower. Now this is a snapshot. You can see all the winds coming with the same speed, but somehow the winds that passes through the top of the wing have a faster speed than the winds that is below the wing. Now that remains, that difference remains even when all the winds have, all the air has passed through the wing. Okay, you can see even up to the end, up to the another end, the wind speed at the top is still much faster than the wind speed at the bottom. So that causes a pressure difference. Okay, is that okay? Now here is the snapshot that I just displayed for you. Okay. Now so we apply the Bernoulli's equation to calculate the lift force. Now the difference in pressure will be the difference between these two terms. Half rho V1 squared minus half rho V2 squared. Okay, the pressure at the base minus the pressure at top will be equal to the difference in the half rho V squared V1 V squared term on both sides. And we define the lift force as a difference in pressure multiplied by the area of the wings. That is a surface area of the wings. And I can replace P1 minus P2 minus P1 by this guy. I extract a constant rho A, and that becomes half rho A V1 squared minus V2 squared. Experimentally, I find that for a wide range of velocity, I find that the difference between the two square of the velocity is proportional to the incoming airspeed, the square of the incoming square speed. That is the experimental fact. Okay, and so I can assign a constant, which is called CL. Okay, so that V1 squared minus V2 squared is equal to CL V squared. CL V squared is the incoming airspeed. That is the airspeed when the air is very far away from the wing. And the constant CL is called a coefficient of lift. It's actually not a constant. It depends on the shape of the wings. And it also depends on the angle of tilt of the wing. Okay, I will discuss it later. And with this definition, I can write the lift force as 1/2 rho A CL V squared. Now you can see this equation. It's actually very similar to the equation for drag force we learned in chapter 4, I think, right? You also have a coefficient, but that is called coefficient of drag. Now you have a coefficient of lift, right? And all other dependencies are almost the same. Half rho AV squared. The equation also reads half rho AV squared. But you notice that the area is no longer the frontal cross-section area, but the area of the wings, okay? The area of the wings that is exerted by the lift force, okay? So the area means different. It means a different thing, okay? Now, if the velocity of air is low, if the airplane is flying slow, then you have to find methods to increase the coefficient of lift in order for the lift force to be enough to lift the whole plane. So how do we do that? Now, people have two methods to increase the lift coefficient. The lift coefficient can be increased by using a large angle of attack. The angle of attack is the angle that the wing makes with the incoming air. So if the incoming air goes horizontally, the direction of the wing goes like this. The angle between them is the angle of attack. Experimentally, we find that the larger the angle of attack, the larger the lift coefficient. So it will be more efficient. The incoming air will provide more lifting force to the airplane. So the airplane will be more easily lift up. And that exactly happens when you see an airplane take off. When the airplane take off, the wing is not in a horizontal position. The wing is slightly tilted at an angle. And that exactly provides a larger angle of attack to increase the lift. Okay, so you can see the airplane take off like this, but not this. Okay, but not this way. The wing is not horizontal. The wing is always tilted upwards, so as to increase the angle of attack and to provide extra lift. Okay, and also you see device called wings flap. When an airplane is trying to land or to lift up to take off, you can see the wing flap will be lower, so that the shape of the wings will change. The rear part of the wing will be lower, and in this way, the cross section of the wing will change, and it will also increase the lift coefficient. Again, it makes the airplane more easy to be lifted up. So with a low velocity, if the velocity is low when the plane is taking off, you need a larger coefficient of lift for the plane to take off, and that can be achieved by increasing the angle of attack and lowering the wing flap. Okay, does it make sense? Now, in your homework, you are going to estimate the takeoff speed of Airbus 340. Okay, and from the takeoff speed, you've given acceleration, you can estimate the minimum length of a runway, and you will find that the length here will be about the same as the length of the runway in the Lantau Island Airport. Okay, so that makes sense. Okay. Now, before letting you go, I will let you see this figure. Now, this is a app. This is a mobile app called Wind Tunnel. You can actually get the free version. For the paid version, you have to pay about, I think, $20 or something like that. Now you can see it displays a streamline. Okay, you draw a wing, and it displays a streamline. I answer a question later. Okay, you draw the streamline, and you can also display the what? Here is the speed distribution. The wind speed here is larger. The wind speed at the below is smaller. Okay, and this displayed with different color. Now there is the display with the pressure. The pressure here is lower. The blue part is lower, and the red part, the pressure is higher. Okay. Now somebody asked me. I cannot finish this slide, but never mind. I'm not in a rush, so I prefer to leave it to the next lecture. But I answer your question first. I heard that, in fact, the major part of lift force comes from Newton's third law, the reaction force of air. That is not true. In fact, the third law still holds, but the third law actually gives a give an effect that is equivalent to the difference in pressure. The difference in pressure actually is the same thing as Newton's third law. Now, what happens about Newton's third law? If the air fly passes the wing, the airstream is being directed downwards. So there's a change in velocity of the air. Okay, the velocity originally flowing in the horizontal direction, but after passing through the wing, it's being directed downwards. So there's a change in velocity, there's an acceleration. And by Newton's third law, if the airstream is being pushed downwards, you have a reaction force on the wing. And so the wing will be lifted up. Okay, but that is equivalent to the pressure force acting on the wing. They are just the same description. They are just the same, but different description of the same physics. Okay, now, but be careful. Some people say, well, if you tilt the wing like this, then you have air colliding with the base of the wing, and that gives you the lift force. That interpretation is completely wrong. Okay, it is not due to the collision of air with the base of the wing to provide the lift force. Why? You see this diagram. You can see actually when the air passes through the wing, the reduction in pressure at the top of the wing is actually larger than the increase in pressure at the base. So it is not actually due to the lift force is actually not due to the increase in pressure at the base of the wing, but more due to the decrease in pressure at the top. It's a purely hydrodynamical effect. You cannot use your concept of a ball colliding with, just like a ball colliding with a plane to describe that lift force. When you calculate the net force acting on an object in an aerodynamic sense, you have to integrate the pressure. You have to do a surface integral of the pressure throughout the whole wing to find the net force. Okay, you cannot rely on the pressure force only at a certain position. Okay, so that is the meaning of that. Any more questions? A very good question from you. Okay.